What I'm going to do is I'm going to, a little bit by the seat of my pants, do a calculus-based introduction to physics and the concepts that we explore in physics. And I'm going to do this with the mentality that I'm putting people in position to not be completely taken aback when a calculus thing comes up in a physical chemistry course. So this is what I'm going to dub my Physics for Physical Chemistry preview. And it's meant to be viewed at any point between now and the end of the first week of the term. Now, I'm making it available over the summer so you can have extra time to muck around with it. But I'll just want to give some definitions and give some relationships between those definitions that we build on when we actually do a calculus-based story in physics. Let me go into kinematics and the study of motion, and let me talk about the three key terms in the study of motion. The first of those terms is displacement. It's how far an object moves along a numbered line. It's represented with a delta x, which is some final position minus some initial position. And it's measured as a distance. It's measured in units of meters. So we put out some number line. This is not a number line at all. And it's halfway the number line. It's a quarter of the way down the number line. It's eighth of the way down the number line. And we'll define these positions as 0, -1, -2, -3, -4, 1, 2, 3, 4, all in units of meters. And the units are implied in the other values. And if we start at a position of -2 meters and travel to a position of 3 meters, delta x is equal to 3 minus -2, or 5 meters. And if we change our color a little bit and start at 1 and travel to -3, the displacement there is -3 minus 1, or -4 meters. And those displacements represent vector values of how an object has moved in whatever period of time it's moved in this particular number line system, right is positive, left is negative. And so the first object moved from left to right. It moved in a positive direction. The second object moved right to left. It moved in a negative direction. And the computations we did along those lines imply that. And the signs represent that these are vector quantities. And sometimes you will actually see these values have little arrows over their heads, which imply the vector nature of the motion. I won't do that all the time here because those symbols can get really superfluous. And we don't deal with a whole lot of vector quantities in chemistry. But we do need to recognize vector quantities as they exist in other elements of physical motion. It will come up and it will be an important thing for us from time to time. So that's displacement. That's our first kinematic quantity. That's our first property of motion that we describe. Our second property of motion is going to be velocity. For those of you who've never had me before, I am random in how I use colors. So I beg your forgiveness for that in advance. Velocity. In general, we describe velocity as rate of change of position. Okay. Now, we can describe velocity two different ways in the full mathematical description of that. Those of you who've had a very good algebra-based physics will recognize the average velocity concept, which is frequently notated as v bar. Another reason not to put the arrows on top of everything, sometimes the bar over average velocity helps to make that quantity very, very easily described. And the units of velocity are meters per second. Abbreviate m/s. And we can tell our number line stories very effectively and tell how our object with -4 meter displacement over a time of 2 seconds that our average velocity is going to be -4 meters over 2 seconds, -2 meters per second. Nothing surprising, nothing dramatic there. That's an average velocity. And average velocities are large-scale pictures of how an object moves from one place to another. But we don't just want to talk about how an object moves from one place to another over a broad period of time. We want to talk about very distinct velocities at very specific moments in time. And that's where the calculus comes in and reduces these extended deltas down to differential values. And that's the instantaneous velocity idea. And we'll have more to say about that as we move forward. When you've told kinematic stories in algebra-based physics before, you've come across the constant acceleration kinematics relationships, and you've identified initial velocities and final velocities for various stretches of time. And part of the challenge of solving problems dealing with motion in an algebra-based physics is the challenge of identifying initial and final velocities. What you're going to find as I tell these stories here and do the stories that prepare you to deal with physical chemistry is I'm going to deal with this far more as a derivative and help you manage the manipulation of functions of time. But give me a moment or two and I'll get to that. The third term is acceleration. And note that I define acceleration as the rate of change of velocity. It's most common to get velocity and acceleration confused. And we need to be treating the concepts of velocity and acceleration with great care as we have conversations about them. Velocity is how quickly a position is changing. That's the classic, how fast are you moving? Acceleration is how fast velocity is changing. Whether your rate of change of position is increasing very slowly and you're building up speed very gradually, or whether you have the accelerator on your car floor and you're speeding up over a very fast period of time, you're feeling pressed in the back of your car seat, or whether you're slowing down, your velocity is changing in a different fashion. Now, in algebra-based physics, we don't usually talk about an average acceleration. We just simply say delta v over delta t, and we're done with it. And we don't typically say average acceleration because most of what we do in algebra-based physics is we deal with constant acceleration kinematics. Problems where the acceleration over a period of time is constant. And again, the units of acceleration are meters per second over seconds. Meters per second per second. How much is the velocity measured in meters per second changing over every second? And you'll see that very frequently written as meters per second squared. And we can deal with a situation previously that if we know that the velocity is changing by some amount over a period of time, we divide that by the time we get the acceleration out. Now, if the object we were studying before was moving at a constant rate, it was moving very steadily at -2 meters per second all the time. Then its change of velocity wound up being not much of anything. But as you might guess, we're in the business of dealing with functions. And we're going to be in the business of talking about instantaneous accelerations as well. And the first thing I'm going to say to y'all who have had algebra-based physics experience is there are very few situations that I'm going to describe here where I'm going to describe tactics that limit ourselves to constant acceleration situations. One of the powers that's concerned with using the calculus to describe these types of situations is the fact that we can talk through some structure of how accelerations result from velocities in distance position functions, and how we can describe not merely constant accelerations, but accelerations that change as well. Let's give some examples. Most kinematic stories we can describe as beginning with a position function. And I'll tell you about a very common position function that we come across when we're studying some kind of kinematics motion. The function that I'm going to describe will look like this. Excuse me. Let's go there. Let's build a function that starts with a term that looks like an acceleration and a second term that looks like a velocity. And let me make sure that I have my units nice and neat. Meters per second there. That's not as neat as I want it, but it'll do. Well, first off, what does that function actually look like? It seems to look like, if I plot out x versus t, it seems to look like something that's got an upward slope initially, but the t squared is going to have a parabolic shape to it. It will let me be a little bit more. It will go up and increase, but level out, and then start to come back down. And b, because of the negative sign from the coefficient of t squared is going to come down here, concave down. If you know how to plot a thing like that as a function of time instinctively, that's wonderful. You know, I'm all about that. If you don't know how to plot something, now, I just honestly gave this thing some initial height too. Let's throw in an additional term, because it looks like this guy's starting from like 5.0 meters. Yeah, let's add that in. Call that 5.0 meters right there. Because when t is equal to 0, that's not sitting at the origin. That's saying some height in the air. It's saying some height in the air where the thing could be thrown up a bit. For very small values of t, the positive term is going to dominate. And this thing's going to keep climbing up. But as t gets gradually bigger, the negative term is going to dominate. And this thing's going to head down towards 0. Okay? So that's what x against t looks like. Let's talk about the velocity of this guy as a function of time. Velocity is dx dt. Let's take the derivative of each of these terms. Negative 4.9 meters per second squared times t squared. I take the derivative as function t of a t squared term. The 2 is going to come down front and multiply by the coefficient here. And this acceleration looking like thing is going to behave like a coefficient. I'm going to multiply 4.9 by 2 and get 9.8. Take the derivative of a term that's just in t. Well, that's a 1 that's multiplied by 2.5. The 2.5 stays. And I multiply my implied term times t to the 0 power. Well, the 0 is going to come down, multiply by this guy, and that's going to take the whole thing away, and that term's not going to be there at all. So the velocity as a function of time is 9.8 meters per second times t plus 2.5 meters per second. Well, let's sketch out a velocity versus time function. V is equal to negative 9.8 meters per second squared times t plus 2.5 meters per second. Well, I'm going to start here at 2.5 meters per second, but I'm going to have a negative slope to this guy. This guy's going to keep going down over as a function of time. Make that a little bit starker of a color. I don't know what your blue and purple combined look like to you. They don't look like anything to me, but a starker line. Because this is a y equals mx plus b form, right? Instead of y, we say v. The slope here is equal to negative 9.8 meters per second squared, which those of you with a good chunk of physics experience would recognize. That's the free fall acceleration. And the intercept here is the initial velocity. Started from 2.5 meters per second, and we came across that way. Now, regardless of what your experience is in this stuff, I would expect that you'd have the capacity to do this with a line. Well, let's remind ourselves again, the acceleration is equal to dv dt. Now let's take a derivative again. Well, t to the first coming over, that's just going to leave negative 9.8 meters per second. And 2.5 meters per second times t to the 0, to take the derivative of that, well, that just cancels out and goes away. And so the acceleration is just as a function of time, it's just horizontal line stuff, negative 9.8 meters per second squared. Okay. And what we've gone and described with this function is the free fall after an object starts in the air. Not after. At a height of 5.0 meters. With initial velocity of 2.5 meters per second. Now, in an algebra-based physics course, we take all of that context and stuff it into a single problem. With function thinking, with the tools of the calculus, we can take this thinking and put it in terms of a function. And put it in terms of negative 4.9 meter per second squared. Half the acceleration is a coefficient of t squared, as it turns out, plus 2.5 meters per second times t plus 5.0 meters. And everything in that function points to a specific property. The coefficient of t squared being half free fall acceleration indicates free fall. The distance by itself indicates height. The coefficient of t indicates initial velocity. Oh, well, if you've done constant acceleration kinematics before, you're very familiar with 1/2 at squared plus v naught t plus x naught. That structure is immediately suggested by the calculus, by the taking of derivatives successively to come up with initial velocity in time. And what I think I want to do with the next video in this series is give you some additional insight into how functions of this sort can get you kinematic quantities you can do problem solving.